We have the following problem. A skateboarder rests at the top of a 25-meter ramp. Without accounting for friction and air resistance, what is the skateboarder's speed at the bottom of the ramp? Now, when you initially look at this problem, you might think we don't have enough to be able to solve it, but we do. So we have to use the energy conservation, which is kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Now this is just a relationship between kinetic energy and potential energy. So on the initial side, sometimes your kinetic energy might be high and your potential energy might be low, but they will be interchangeable. So on this side, kinetic energy might be low and potential energy might be high. It just depends on the situation. But in this situation, it's the opposite. It is the potential energy is high because we're on top of a ramp, and the kinetic energy at the top, we're at rest, so it's low. And then, as we go down the ramp, our kinetic energy goes up, and our potential energy goes down because we're basically trading that potential energy for kinetic energy. So that's what the energy conservation is. So now, how do we get these things? So we know kinetic energy is 1/2 mv squared, and then potential energy is the mass, which we're not given, and then it's gravity, but we know gravity is just 9.81 meters per second squared, and then it's times the height, which the height in this case is 25 meters. And then equals kinetic energy final, which is 1/2 mv squared plus potential energy, which is still the same, mgh, but at the bottom of the ramp we know it's 0. So this whole thing, if this is 0, anything times 0 is just 0. So this whole thing does not matter. So what this would look like is just like you have a skateboarder sitting at the top of a ramp, 35 meters high. So you got a person sitting up here. So they'd be more like, but basically, so right now they're at their peak potential energy. So potential energy is high at the top, but then as they go down this ramp, their kinetic energy increases. So I don't know if you can see that or not, but then when they get down here and their height is at 0 at the bottom of the ramp, their kinetic energy is high while their potential energy is low, because in this case our potential energy is all coming from the height, so the distance the skater is off the ground or off the ramp basically. So reset. So right here we see this is why we can do this type of problem with only given the height. So we have 1/2 mv squared on this side, and we have 1/2 mv squared on this side. So we know that this cancels here, this mass cancels with this mass here, but also we know what the velocity is on the top of the ramp because it says they are at rest, so this also gonna cancel out because this is a 0. So this whole thing cancels because 0 times anything is just 0. So what we have is we have 9.81 meters per second squared times 25 meters equals 1/2 velocity squared. So now I'm just going to type that into a calculator. So we have 9.81 times 25. We get 245.25. So equals 1/2 velocity squared. So from here it's pretty easy. You have to multiply, or technically you divide this side by 1/2. So you divide by 1/2, divide by 1/2, but we know dividing by 1/2 is the same as just multiplying by 2. So 245.25 times 2 equals 490.5. So we have 490.5 equals velocity squared. And we just take the square root of both sides to get just v, and we get velocity equals 490.5 square root. We get velocity equals 22.147. So velocity is about 22.15 meters per second. And this is the velocity when the skater has already gone through the whole ramp. So this is the velocity that the skater gets down here. So yeah, that's a simple example of an energy conservation problem and how they work.